Were you recording, Eric? Did I just? Maybe I just stopped it when I hit the button.
Oh my gosh.
I would.
I think
Stop it, you man.
No, I just restarted it. I don't know.
No,
if
that's okay. It's all right if you restart.
We'll check it
Are we
after.
on now?
We're on now, yeah.
Because when I put this on YouTube, I have to break up into 20-minute chunks anyway.
hey, look.
So, yeah,
So it's
that's
fine.
all right.
This guy. This guy.
Holy hell! There he is.
Hold on. Oh,
There's
there.
Nernst. Thank you.
You can turn your brightness back down now.
Does he look like a
You
nurse?
can turn your brightness
Yeah, he
back.
looks like a nurse.
Oh, you did turn it up. I didn't even know.
So you could see it on the screen.
All right.
So whatever.
Now coming back to our sketch,
catchphrase of mine.
I want you to keep that in mind. Standard conditions are for one molarity of everything, including products. Also keep in mind that concentrations are constantly changing. What do you think is going to happen to the voltage over time as the current flows? It's going to go down. Yeah, because you're going to have less reactant to give off the electrons.
So you don't
And so the longer this goes on, the less of the reactant you're going to have, the lower the lower the concentration, and the smaller the voltage. The voltage will go down over time. Yeah.
So wait, so this means that not everything can go for a redox equation, only like certain specific ones, right?
Yeah.
Because because you might accidentally.
Only when oxidation numbers change and electrons are either
Is
given
it
off or
possible
taken.
that you accidentally take an electron from other reactants other than?
That's possible. I guess if you had something that wanted to oxidize, if you have manganese ions and let's say you had sodium, the metal, in here. The sodium oxidizes way easier than manganese ions do. So yeah, you can have more than one thing oxidizing, I guess, if you have a mixture of reactants. Now, what's the line notation going to look like in this case? I erased everything I wrote before, but you remember how the electrodes have to be on the far left and the far right?
Yeah.
So we're going to have platinum on the far left, because that's the electrode in the anode, and platinum on the far right, because that's the electrode in the cathode. And in the middle,
You just put commas in between all the different.
yes, that's right. What you're going to do, it would be a platinum electrode there. Now the platinum is the only thing that's solid in the anode, isn't it? So that's where the line comes in. And then everything that's aqueous is over here. Put the reactants first and then the products, but separate them with commas. That's just the way line notation is done. Can you see that in there, Eman? Is that
The
pretty clear, the
board?
board?
Yeah.
Okay.
What happened to Eric?
He had to go to the bathroom.
Let's see. So we have at the anode, copper plus 2, comma, is going to make permanganate, but it also makes hydrogen gas, not hydrogen gas, hydrogen ion. So include those. And it doesn't matter what order you put the two products in. You see how both of those go in there. You can put the hydrogen first and then the permanganate if you want to. It doesn't matter. But you should put the Mn plus 2 first because it's a reactant. Yes?
Ever use line notation rather than?
Not that I know of.
Okay. Question also.
Yes, sir.
Why? How can there be hydrogen in both beakers?
Hydrogen is being given off in this beaker. It's being taken in that beaker.
Wait,
Yeah.
for the
So
cathode.
this one, the hydrogen concentration is going down, but in that one's going up.
For the cathode, is the what's it called? Iodine ox.
Oh, this is periodate.
Oxides.
Periodate.
Yeah. Are those just there for to like give the electrons somewhere?
Yeah, well, this accepts the electrons, and it changes into that. So the I is a positive 7 in this oxidation state. It goes down to a positive 5 in this.
Does it
one.
matter
So
what's
it's
in
reduced.
there though? Because
Yeah, it has to react according to its half reaction. And its half reaction is probably not on there. You'll see it. It'll be. Spencer, go back one slide.
I tried to find this picture.
There is
to
our
write that
half
down
reaction.
for you, but I couldn't
So the
find it.
periodate needs hydrogen ions in order to react to
It
make
was.
that.
oh, I thought that was because I didn't see the iodines over there. So
Oh, yeah. Well, I haven't not. I'm only halfway through this.
Does
Out here,
Yeah.
nothing.
Periodate have the same tendency to
He was
reduce
writing
as
it on the picture
permanganate?
that actually.
Yes, it's better in fact because you can see the reduction potential. Periodate is higher than permanganate.
Oh yeah. Okay. I
So
don't
if you really
have
want
that.
something
Yeah, I
to
don't-
reduce well, use periodate before permanganate. It's not much better. It's 0.09 volts better, but it's better. So permanganate is an outstanding reducer, but there are things that are better.
Okay.
And permanganate is cheap too, which is a plus.
We're all about paying.
Okay, now while we have this slide on here, at the cathode, we're going to use this reaction because we didn't have to turn that one around. So it's going to be periodate is in solution. Hydrogen ions are needed. Those are both reactants, so we put those first in the line notation. And then the product, IO3, with the electrode. So that would be the line notation for that reaction. I didn't ask you to do that yesterday, but that's what it would look like.
And when you're doing these, you never have to balance them?
For the line notation, you don't balance. This problem said, give the overall balanced equation. Now before we do that, take a look. Remember, this thing got turned around. When you add the oxidation and the reduction together, what do you need to make sure is balanced before you
The
add them together?
electrons.
What? The electrons have to be balanced. What are you going to multiply the oxidation through by?
2.
Yes. Yes, because you got 5 given off. Remember, this thing was turned around. The equation for it's black over there. That gives off 5 electrons, this takes in 2. So you need to get those to be the same, which is 10. So multiply the first one by 2, the second one by 5, and then add them together.
So
Spencer, let's go on to the next one.
So we don't put any of the coefficients there at all?
Not in the line notation, but in the chemical equation, of course.
Okay.
Right? And when you add the two together, remember, like always, some of the hydrogens will probably cancel out. The waters may cancel out. We were left with a net number of waters over here on the left.
Also in the cathode and anodes, do we put the elements together as well, the similar elements? So say like you get manganate with manganate, and then iodine with iodine.
In the line notation?
In the, line notation and
No, in the line notation, you want to put reactants first and then products second.
Yeah, but I'm saying like, do you want to put like the
Oh, I
compounds
see,
with
the way I
similar
did that.
elements?
No,
Yeah.
you don't have to, like in that case. I don't have them together, it doesn't matter. Just make sure you put reactants first and then products.
Okay.
Anything else about this example? You see how I got 0.09 volts? We had to turn that first reaction around, so negative 1.51 plus positive 1.60 gives us 0.09.
Oh, what do you want us to put in salt ridge when you're talking about like the flow of electrons?
The salt.
Just like this, I don't need to see what the ions are, just say that the negatives are going into the anode, the positives are going into the cathode. And that's always true. Because the anode is the loss of electrons, so you build up positive, the negative from the salt bridge has to go every time.
Okay.
And same thing for the cathode. All right? I have something that's fun.
Oh. Potatoes.
We have a clock. How do you like my clock?
Oh, it's so cute.
It's different from the other one.
Can I put a on that or something?
There's no battery in the clock. Is that obvious here? It's not working. The board behind the clock here it has a couple of wires. One of the wires has a zinc terminal to it, and the other one has a brass terminal. Brass is mainly copper. The zinc can send electrons into the copper. And they need a medium through which to go. So if I take the zinc electrode here and stick it into the potato. Now, if I put the brass one also into the potato, in this case, it's not going to be enough electron flow to get this clock to light up. So what I have to do is I have to use 2 potatoes. And the reason I'm using 2 potatoes is because I have a second wire that's got a zinc end and a brass end. So, in this first potato, I have the zinc stuck in there. I'm going to stick the brass in to the same potato, like that. Now the zinc is sending electrons over to the brass. Doesn't help the clock though, because the clock is still not completed. The circuit for it is not completed. So I take my other potato. I got my one.
You're not cooking with these tonight, are you?
You have to come and find out. So I got a zinc now lead in this one, and now the brass that was originally out of the clock. Can you see that clock? This is so good. Put the brass into it over here,
Oh.
Whoa.
and what do you see? Oh, where'd it go? There it goes. The clock turns on.
Oh, no, no.
It's
I
off
got-
and on.
Oh.
I mean,
Yeah, that
it's
should do it.
on.
So yeah, the clock turns on. This actually has enough current to run the clock. No battery. I don't have any external source of energy except for the 2 metals. The potatoes really aren't even providing any energy. What do the potatoes do then? That's like the salt bridge. That's the conductive medium that the electrons can flow, through which they can flow.
Wait,
What's
so
on?
what?
Then you run out of energy.
Yeah, eventually the potatoes dry up. Every time I stick it, the leads get wet. It is losing water. They'll shrivel and it'll stop.
Wait, so why are we powering our cars with vegetables?
These are very weak.
Over time, the zinc gets small and it just corrodes. So yeah, I mean, for a temporary ride, you could power it with vegetable liquor.
E-man.
Yep. A week from today, on Friday. Listen to this. On Friday next week, we're going to have our annual battery lab. You need to bring in things from home or from the store that will give you a redox reaction like this. I got zinc and brass. Watermelon can serve as the salt bridge. People bring in grapefruits and lemons and oranges to serve as salt bridges, potatoes. Your goal is to try to use as much, or try to generate as much voltage as you can. Now, on Friday next week, you can use 3 cells. This is a 2-cell system where I have one potato with the zinc to the brass, and then the next one from zinc to brass, and then going back into the clock. You can use up to 3 in your setup. So you can generate pretty good voltages with 3 cells. And let's see, next week we have our broken up MME week. Tuesday we won't see each other, but we will on Wednesday. Wednesday is going to be mainly a practice day, where I want you to have your equipment that you think would be good for a battery, bring it in on Wednesday, and you're going to have most of the hour to work on it and see how it works. Then if you need to make revisions or get other substances, then you'll have still a couple of days to do it. So it's a great thing to do on our MME week because you get some time to think and plan and try. I'll have voltmeters out that day. The only 2 things you can't use are lithium. You can't use any lithium. You may want to research too. If you want to be the best voltage in the class, you're going to get extra credit. You know we don't have extra credit for that. The highest voltage in the class gets a 15 out of 10 lab grade.
Wow.
The second highest gets a 13 out of 10, and then the third highest gets a 12 out of 10. If you're the highest voltage in all 6 chemistry classes, then you get a 18 out of 10 for being the grand champion. So that's coming up, and you're going to want to maybe do a little bit of research and find out what materials would be good.
Wait, can we use actual
2 things before you ask. 1, no lithium allowed. And you can see lithium is at the very end of that reduction potential table.
Sorry.
The other thing is you may not dissect real batteries.
Dang
Because
it.
isn't that what they did last year? So it's
A couple of years ago they did. Yeah, we had people catching on fire while their things were catching on fire. Taking lithium out of a lithium-ion battery, very dangerous. I don't want you to do that. And so no batteries, no pure lithium. Anything else to go goes.
I once opened a car battery before. Very delicious liquid.
No mixing bleach with acid. That's the Bolino rule. Clears the room. We don't want that. It's very toxic. It's a funny memory, but it's very nasty to breathe chlorine gas. Makes chlorine.
Why would he make
I still don't know.
Even I don't know.
We still joke about it, and I still don't know why he added that. I told him twice that hour, Bolino, you're not going to put the acid in the bleach. Oh, no. So then, I look over at one point in the hour, and there's this big yellow cloud coming up. And Bolino's laughing right at Omkar. Like, Bolino! If you know Omkar, you can just see this.
What kind of acid did you use?
Hydrochloric. So yeah.
You could have at least used like a week acid.
Then we had last year, this was not anything, I wouldn't say this was a mistake, it was just something that he didn't know. Jason G had some concentrated hydrochloric acid, which you can buy at a hardware store. It's called muriatic acid out there in in hardware context. So you can go to the hardware store and ask the guy, hey, I need muriatic acid, and they'll send you right to it. But anyway, Jason had some aluminum, and he added the hydrochloric acid to aluminum, and it reacted super fast. He had a real high concentration, a lot of aluminum, and he had this big cloud of hydrogen gas coming out. It was so much that we were having trouble breathing. That also cleared the room. Yes!
We've been waiting for this all year.
We're not doing that. Tarun?
So for them, does it mean that they have to do it again? Or